Cool, and we are live. Hey all, I am Wyatt from McMaster Competitive Programming, and you are here today for the 2021 ICPC Tryouts, which will determine who we send to the East Central North America Regionals. So I am joined here today by Daniel, who is the former MCP president, and Mikhail, who is our resident pro competitive programming alumni. And I'm going to let you guys take it away.
Thanks, Wyatt. So yeah, this is MCP tryouts for ICPC 2021. Daniel and I had a lot of fun preparing these problems and this contest for you guys. We're really excited to have you guys try out the problems, and of course excited to see who makes the team. Daniel, do you want to tell us a bit about the format of the contest, how this is going to work?
Yeah, sure. So we have prepared 9 problems for everybody. There are going to be 2 easy, 4 medium, 2 hard, and 1 advanced problem. Now, I just want to put a disclaimer here. Wyatt has never seen these problems before. He was not part of the process. He's only here for the beginning of the stream. Then we're kicking him out so he can go compete along with the rest of you.
I do have a very obvious conflict of interest here.
Yeah, yeah. He has not seen anything. He has not touched the contest at all. That was only me and Mikhail. But yeah, so the problem distribution is there's 2 easy, 4 medium, 2 hard, and 1 advanced. All these problems have different points allocated to them. So, for example, the easier ones will have lesser amount of points, the medium a little bit more, harder ones a lot more, and the advanced one will have quite a few points that you can get from it. So you'll notice when you enter the contest that the points don't just steadily increase based on difficulty. We've allocated points based on how much time or how difficult the concepts are behind the question. It doesn't mean that it's strictly more difficult. So if you're better at graphing than you are at math, then there might be a chance that there's a problem later into the contest that would be easier for you than the one that's marked as easier, technically.
I think it's good to mention as well that the order in which the problems appear in this contest are not necessarily the order in which you should attempt them. Like Daniel said, some of the problems require different sets of skills, so it's very important that if you get stuck on a problem to just move on, and basically try not to get stuck. It's very useful in these tryouts as well as the actual ICPC contest.
It's also really good to mention that all of these problems have partial point scoring. So if you don't know the full solution or the most efficient solution, at least give it a shot. You might get at least half the points or something like that, and then you can move on to the next problem. So it's good to remember that you don't need to get the problem 100% right in this contest. This is not true for ICPC. In ICPC, you have to get the problem 100% correct and 100% efficient. But in this contest, we just want to see what you're capable of, so just do your best, and if you can't get full points for it, move on to the next one, because there's probably more points you can get over there.
Yeah, absolutely. So I guess Wyatt, how do you feel about this contest sort of leading up to it? Are you excited? How do you think you're going to do?
I'm pretty excited. I'm hoping for a repeat performance of last year. That would be ideal.
Can't remember last year.
I don't even know who we did them last year. I think was it IAHS last year? I feel like it was.
Probably.
Yeah, probably.
Vague recollection. Yeah. Okay. I think all I remember from last year was like there was pizza in the contest. And I think Michael, who's like one of our execs, made the remark, anybody who got up for pizza, I was like, you tell people who'd like give it up. It's like, people to get food. The other people like just kept coding.
Nice.
But yeah, I'm pretty excited. I will say though, I'm sort of disappointed. In the past, I always like to bring my mechanical keyboard to the contest. Then right when the contest starts, I like go right into it. It's my big tradition. It's like intimidation strategies, but I can't do that this year because it's all online.
Yep.
For better or worse.
Yep. By the way, Wyatt, I saw that this contest is actually sponsored by Intel.
It is sponsored by Intel. Yeah, they're actually. I don't know if this is their second year or third year sponsoring us. What tends to happen is like I remember back in biology class, you got like those. There's like, oh, this is gonna be a shame because I don't even know the term, but there's like mutually beneficial relationships. It's like Intel gives a sponsorship.
Symbiotic, kind of.
It's symbiotic. Yeah. So I don't know. It helps us. It attracts people. We tend to get like funding, and then it works the other way in that I guess Intel gets like often like good hires or people they can interview for internships and like full-time positions, which they like.
Awesome.
Yeah, and I also saw that there are prizes actually beyond just participating in ECNA.
Yeah. So if I must say, I think our prizes are better than the ECNA prizes. ECNA prizes is only a backpack. It's not really that exciting. Our prizes, we got some cash money for the top 3 people, and and t-shirt prizes for the top 15. Let's get your own MCP t-shirt.
Yeah, awesome.
Well, I think we should mention that we highly encourage everybody to keep the stream open, even if it's just really quiet in the background, because if any problems come up during the contest, we can make an announcement that way and let everybody know as soon as we can. HackerRank does have this notifications feature, which we used a couple days ago to let everyone know what the actual time of the contest is. And we can try and use that, but we don't know how great it is. So you can also keep an eye on the notifications tab in the top right of your browser. Hopefully you can catch any notifications if we need to send any. We had people go through and test the problems, so we don't expect any problems or any issues.
Yeah.
Big
thanks to Michael and Tio of UFT fame for that. Very helpful.
It was very good stuff. Yeah, and then after the contest, be sure to check back in on the live stream because Mikhail and I are going to go through and just cover the general concepts and solutions for every single problem in the contest. So if you're interested in, if you're stuck on something, you want to see what the actual approach is, then you can come back and check it out.
Yeah.
I'm excited for that. I heard you guys have a Jamboard prepared as well.
We do have a Jamboard prepared.
That's right. I think it's also a good time to mention as well that if you do have any questions during the contest related to a specific problem, there should actually be like a discussion tab for each problem where you can post your question, and we'll sort of be monitoring those and replying there as well. So if there's something that you think isn't clear, or something which you think is wrong, basically post a message. We'll take a look and then
you can also send a message in the chat here if you want to do that as well. If you want to get us, it's probably a little bit more efficient to get our attention here, but we'll see. We'll do our best to keep an eye on the forums and stuff.
Sure. Yeah.
Yeah.
Yeah. So.
I guess Wyatt, you might want to go start getting ready.
Yeah, honestly, I'll probably head off. So I wish you guys luck. Yeah. Peace out. And hopefully I won't break your streaming setup when I close this tab.
I don't
wish you luck. Okay, good.
All
right, good. All right, see ya.
Thanks, Wyatt.
All right. Okay, yeah. Nice. Just me and you now, and everyone else watching.
So yeah, if anyone has any questions, feel free to drop that in the chat, and we'll try and answer that. But until the contest begins, I guess we'll just be kind of chilling.
Yeah. What do you have any predictions for the contest? Like, do you think that, let's say, like everyone will solve at least one problem, or do you think that there'll be someone who solves all of them?
I don't think anyone's going to solve all of them. Yeah.
Bold.
I mean, I'm pretty confident no one's going to solve every single one because there is 9. So even if you are capable of solving all of them, the harder ones are going to take you at least 30 minutes, I hope. And that's, the majority of the contest already. So we think just by sheer volume, you won't be able to solve all of them. At least that's what I think. What do you think?
Yeah, I think I have to agree with that prediction. I think that, there is a chance that we'll get a full solve, but it's quite low. And I think, we kind of did that on purpose, right? We don't want we'll just finish early and be, oh yeah, I'm done. Time to grab lunch or something.
Yeah, it's not ideal. That being said, I think the majority of people will solve at least 3 or 4.
That's okay.
Yeah.
Interesting.
So there might be a speed aspect there, but once again, don't rush yourself.
Yeah, well, actually, speaking of speed, we mentioned that you get points for solving test cases and problems. I don't think we actually mentioned how ties are broken.
Okay.
Now, probably should look this up beforehand, but I think the way it works is that your time penalty is basically the sum of the times of your best submissions for each problem. So what that means is that, if you solve all the test cases of a problem, the time which you made that submission, like in seconds, basically becomes your penalty score. So obviously, if you solve the problems faster, it's better for you when it comes to tie break.
Yep.
And if you make a submission where you get, say, half the test cases, and then make a later submission where you get all of them, then the time in which you made that last submission, basically your best one is the one that's taken.
Yeah, it looks like that's what the scoring says.
Awesome. Great.
Yeah.
Yeah, that's a good thing to sort of keep in the back of your mind. Obviously, you can view the leaderboard at any time during the contest.
I hope everyone's familiar with HackerRank. If not, this is a great time to get familiar with it because if you have any interviews coming up, they might send you a HackerRank coding test. So this is a good chance for you to get familiar with the interface.
Mm-hmm. Yeah, absolutely. And I guess just to help some people out, people might notice that for each of the problems, we actually have code already written for you to basically get the input and print the output for you. So all you need to do is actually write the algorithm that solves the problem. Yeah, because actually, Daniel, do you want to comment sort of on why we did that?
Yeah, so there are a few problems that will require you to output a double or a float. And we need you to output that double to a specific precision. And not everybody knows how to output a specific precision in the language they want to use, which we should cover which languages we're covering after I finish this. But yeah, so we provided templates, or like basically you just fill in a function, kind of like on LeetCode. If you've ever done a LeetCode problem, they'll just give you the function and the input is the parameters, and then you just return the result. We're doing the exact same thing here. So we pass you everything you need in some form of data structure or just a bunch of parameters to the function, and then you just need to fill out the logic and then return your result, and we'll handle outputting with the correct precision or with a correct format, so you don't have to worry too much about that. If you want to just ignore those functions, I know some people don't like using those functions, you can just delete the whole thing and take input yourself. We do provide a description of how the input is given to you in the problem statement, but if you are perfectly fine with using the functions, we highly recommend you use them. That way you don't have to worry about taking an input, and you get to save a little time that way.
Absolutely. Definitely going to be some people, I think, which are going to be, maybe using their own templates for that.
Yeah.
Something, though, that we should mention, what languages are supported.
Yeah.
And yeah, so basically the languages supported for this contest are going to be the same ones supported for the actual ICPC contest. So this means that acceptable languages are C, C++, Java, Kotlin, Python 2, and Python 3.
Yep.
Yeah,
We support both Python and PyPy in both versions 2 and 3. So we recommend if you are going to use Python to use the PyPy one instead because it is a little faster for most cases. But you're free to use either one.
yeah, like the correct solution to each problem will be doable in whatever version of Python you want to use.
Yep.
Probably mentioned that, so yeah,
Right.
feel free to use whatever you're most comfortable with.
Yeah, we're coming up on 1 minute left to the contest, so I hope everyone's ready. We're excited for all of you. This is an exciting moment. But yeah, I guess we should just uh, fade out to some chill lo-fi music and wish you the best of luck then.
Yeah,
All
for
right.
sure. Best of luck to all participants.
Good luck, everyone.
Enjoy.
everyone, just a reminder that you can only use libraries that come default with a language. HackerRank doesn't support third-party libraries or any other libraries that don't come default with whatever language you're using. Also, the only online resources you're allowed to use are official language documentation. All right, good luck, everybody.
actually.
All right. That wraps up the contest, everybody.
Yes, congratulations on making it through. Hope it was a fun 2.5 hours. Yeah, it was. I mean, I don't know. I'm sure Daniel can say the same, but we had a lot of fun sort of moderating the contest, looking over the submissions, seeing the leaderboard change. I think we're actually quite happy with like the distribution of scores. You know, it's pretty close. And I'm getting feedback. Sorry. And yeah. So Daniel, without further ado, do you want to sort of announce the top 15 contestants who will be moving on?
Yeah, sure. So, right off the top, congratulations to Wyatt, Michael, and Alicia Tran, who made first, second, and third place respectively. And I'm going to go through and announce the usernames of the top 15. I apologize in advance if I get it horribly wrong. But we got Mistake in fourth. Love your username, by the way. Simple Happiness in fifth. Yili Liu 7 in sixth. Ayub, Ayubh, I don't know how to say that, in seventh. Luke 97 in eighth. Win XL in ninth. QWERTY MDU in 10th. And in 11th, we got JK Modi. 12th, Hun 41. 13th, Black Cobra 00. 14th, we got SK Vort V. And in 15th, we got Handsome Hanson 21. Congratulations to all of you. I'm sure Wyatt will be reaching out to you about how to get your t-shirts and your prizes to you. I think we're going to pull Wyatt back in eventually. Is that the plan, Mikhail?
Yeah, I think so. I guess the current plan is we're going to actually go through the problems, talk about some interesting things we found during the contest, and of course there are solutions. So stay tuned if you're curious on how to actually solve these problems. Might help you out for next year, actually, if you want to participate again. And if it's a problem that you've already solved, maybe there's actually a different approach, which could actually be better than maybe what you came up with. So yeah, so I think after we go through the problems, we'll let Wyatt back in.
Okay, sounds good.
And discuss maybe some logistics.
Yeah, so if you
T-shirts and
don't
stuff.
want any spoilers to questions, you can feel free to not you don't need to stick around. I believe this stream will be saved on YouTube, so you can always come back and take a look at the editorial afterwards. Wyatt, please correct me in chat if I'm wrong about that, but I think that's how YouTube works. Apparently he can't wait to see the editorial for Flights on Mars. Wyatt, we know exactly what you're doing wrong. We'll get to it. Anyways, so yeah, so
Yeah.
if you don't want to stick around because you don't want spoilers, then feel free to take off, and you can come back later and see what the actual solutions are. There's also, every single problem has a written editorial, so since the contest is over, you should be able to go to the problem, and you should see an editorial tab next to discussion or something like that. And if you go in there, you can take a look and see what our solutions were and what our approaches were. Some of them are really in depth, some of them are just kind of like a couple pointers. But yeah.
Yeah, I guess without further ado, do you actually, Daniel, do you want to do Grand Theft Music, or do you want me to
No, you
take a
should do
stab at
it. We'll do our own questions, just because we know it best.
Okay. Are you looking at the Jamboard, by
We
the way?
are. We are looking at the Jamboard. I'm on page 1 too, I think.
Excellent.
Nice.
Grand Theft Music. All right. So basically, this is the strings problem of this contest. And I should mention that the first submission, which got a fully sort of accepted solution, is Wyatt Wismer. I think just over 3 minutes in. It's a good job to him. And I think actually the vast majority of people who wrote the contest also got this problem, which is nice actually. It's good when everyone at least gets one problem. At least most people. So yeah, so basically in this problem you're given one string, which we call a copyrighted song. So a song is basically just a string consisting of letters from A through G. So this, for example, is a suspicious song. And what you're given is you're given a set of, sorry, this is your copyright song. Then you're given a set of suspicious songs, which are basically other songs of the same length, which again just consist of letters from like A through G. And what you need to do is you basically need to count how many songs in this list are similar to this one. So basically, songs are similar to their permutations of one another. So in this case, if we compare ABC, actually, let me use the pointer. If we compare ABC and ACB, we can see that they're permutations of each other, because if you swap the letter C and B, you actually get this original copyrighted song. If you look at a different example like GAC, these two are not similar, because this letter G basically makes it so that like, no matter where you put it, you'll never be able to get the string ABC back. And so the solution in a nutshell is basically to go through your copyrighted song A, B, and C, and you count the number of occurrences of each letter. So in this case, we know that for A there is one occurrence of A. Well, for B there's one occurrence. For C there's one occurrence. I guess just to make this more interesting, let's add like another letter. Let's add another B. Just to these. So we'll do like this or this. And now we say, okay, well, for this copyright song, there's actually two B's. So this is basically like a histogram, basically letter counts. And the idea is that if the histogram of two songs is the same, then there are permutations of one there. Then they're similar. So you got something like ACBB, you actually can see, okay, yeah, there's only one A, there's only two B's, and there's one C. And because they match, you know that they're permutations. And the reason why is you can imagine like taking each of these letters and basically like removing them, like putting them into some kind of bag. Like imagine they're Scrabble letters. You put them all in a bag, and you can sort of put them out one by one. And basically, if in this case you have like one A in your arsenal, two B's, and one C, if you want to reconstruct ACBB, you take out your A, you take out your C, then you take out your B, and then your other B. And yeah, basically, if the frequencies count, then it's a good solution. A slightly more elegant approach, actually, you can also just sort the songs. So you can sort this one and get basically A, B, B, C. Sort this one, get A, B, B, C. And if the sorted songs match, then they're also similar to each other. Yeah, I guess that's the overview. Any comments, Daniel?
No, I think you covered it pretty well.
All right, great. Yeah, so do you want to move on to?
Yeah. So
well, actually,
so the
you
next
want to do
one.
Pesky Rumba later, or?
Yeah, the next one's Pesky Roomba, but since Pesky Roomba has a more difficult version, I think I'm going to save the easy solution for when I do the difficult solution, because the difficult just extends upon the easy one, so we're going to do that all in one go when we get to the difficult one.
Okay.
So do you want to jump to the Solar Cities?
Yeah, sure. So this will be on slide 3.
Okay.
Solar cities. So for solar cities, basically you are given, well, actually let me draw this. You're basically given a number line. On this number line you have houses, MCP homes. And the idea is that you're allowed to like erect two lighthouses, two identical lighthouses, and each of them basically cover some kind of area to each side. So actually, you know what? If I make this an actual number line, this might help for illustrative purposes. So if this is basically 0, 1, 2, 3, 4, 5, 6, 7, 8. We basically have homes at say 1, 7, and like 3. Yeah, we're basically allowed to construct lighthouses at any integer coordinate. So let's say we make two lighthouses, one at like 2, and another lighthouse at like 6. Is that each lighthouse sort of shines light upon everything within a certain distance, within a certain power rating of them. So if the power rating is 2, then you can basically say that this lighthouse at 2 covers the homes at 0 and 1, or the coordinates at 0, 1, as well as coordinates 3 and 4. Same with this one. The idea is that if the lighthouses cover all the houses, then you have your solution. And the question is, how do you basically make the power rating lighthouses as small as possible? So you basically have two things to consider. A, what is the power rating lighthouses? And B, where do you actually put them? I guess the solution, or I guess there are actually several solutions here. I think there are actually 3 in total. one of them which we didn't actually see that some people actually come up with and submitted that we'll, I guess, discuss in a moment. But the intended solution, or I guess the solution I initially intended for this problem, was basically for you to use a binary search. So the idea is that you take the positions of all of the houses. So in this case, say 1, 3, 7. You basically you can imagine just sorting them just for convenience. And then what you do is you ask yourself, okay, what is the minimum possible lighthouse rating that I should consider to see if it works, and what is the maximum one? So say the minimum rating is say 0, and the maximum rating is like, in this case, let's say it's 6. I mean, as long as it's bigger than what you need it to be, then it doesn't matter. So what you do is you basically ask yourself, okay, can a rating of like 3 cover all the homes? And the way you do that is you basically look at the leftmost house, and you basically place a lighthouse, say 3 units to the right of it. So if it's at 1, you basically go look at 2, 3, 4, place a lighthouse here. And you do the same thing for right-hand side. So you take the biggest lighthouse and you place, so you take the biggest home like with the largest x coordinate, and you put a lighthouse 3 units to the left of it. So if this is 7, you put, in this case, it works out to both be 4. So let's change the numbers a little bit. That was unintentional. If we're looking at 2, basically put 2 units to the left, and here 2 units to the right, and here 2 units to the left. And what you basically do is you say that these 2 lighthouse placements are optimal for 2, because the idea is that they basically cover like as much as they can from one end, as much as they can from the other end. If you basically move the lighthouse, if you move the right lighthouse on the right 1 unit to the left, they will no longer cover the house on the right, so it won't work. And same thing the left side. If you basically move the lighthouse 1 unit to the right, then your leftmost house won't be covered. So you know you need these 2 lighthouses here if this power rating were to work. Then what you do is you check to see, are there any houses in this gap in between? And you can actually do that with actually a binary search on the locations of the houses. So in this example, you have the lighthouse at 3. What you do is you say, okay, is there a lighthouse? Sorry, is there a house? Basically, or let me put it this way: is there what is the first house that basically occurs after 5? Because is that this lighthouse at 3, it has a power rating of 2. It covers all the homes up to 5. So you figure out, okay, is there a home past 5 here? In this case, there's one at 7. And the idea is that if this home is not covered by the right lighthouse, then you're screwed. You can't use power rating of 2. You need to do something higher. And if you can, then you try and go lower. Then you try and see, okay, can you do a power rating of 1? Basically, this value divided by 2. Yeah, I'd say like the code in this case maybe is like simpler than trying to explain it conceptually. So this is basically my approach. Daniel, do you want to cover an alternative?
Yeah, so another approach that we saw more people taking, in fact, I don't think we saw anybody take the binary search approach, did we?
Yeah, I don't think I saw anyone.
Yeah, so the approach that a lot of people took was to instead just take that same number line, and what they do is they'd start at the leftmost house. So let's say this is the leftmost house. Let's say it's at position 2, and the maximum one is at 8, and then maybe there's some houses in the middle. So this isn't a number 9. This is just where the houses are, if that makes sense. What they do is they'd start at the leftmost, and they'd say, okay, so what if I decided that this index is my boundary. This is the place where I'm going to split houses. So every house at this position and to the left will be covered by lighthouse on the left, and then everything on the right will be covered by the lighthouse on the right. And what you do is you move from house to house and say, okay, which one is my optimal solution? So basically what you can do is at any index, so let's say we're actually here instead, we can see, okay, look, from this position and to the left we have 3 houses. So you can see, hold on, let me erase what I have here. So we can look and see, okay, look, we have houses from, let's say this is, let's actually give this a value. Let's say this is 5, and this is 6, and then this is 3. Yeah, that works. So we can see from this point on, we have house 5, 3, and 2, and we want to cover these with the left lighthouse. And what we can do is we can take the minimum position of these houses and the maximum position of these houses. So that's 2 and 5, and then put a lighthouse right in the middle. So in this case, 2 plus 5 is 7, divided by 2, integer division, you get 3. So we can put a lighthouse at 3. And then we can do the same for the right side, but we're not going to include the one that we're currently on. So we're going to say this is what gets covered from the right lighthouse. We do the same thing, find the middle point, it's actually 7, so we can put a lighthouse at 7. And then from here we can just say, okay, we know where our lighthouses are going to be now, and now it should be really trivial to figure out where, like, what the power of each one is. So we just need to figure out, if we're at 3 and I need to cover 5 and 2, I know that I need this to have a radius of at least 2, because in order for it to stretch out and get 5 and 2 in this case. And then you can also look at this one. This one only needs 1, but since both lighthouses need to be the same amount, we take the maximum one of this. So this actually ends up being a very clean solution. You can do this with one loop, but you do need to sort the houses first. So you do end up with an n log n solution, which is the same as Mikhail's because of his binary search. However, Mikhail, I don't know if you want to take this, but there are a couple people who managed to do this without sorting.
Yeah, so I should first say, actually, that our first correct submission of Solar Cities was by Yili Liu 7. So big congratulations to them. But we noticed that at least 2 other people, so in particular QWERTY MDU and Win XL, they actually managed to do this without sorting, just like an order n solution. And basically what they found was something pretty clever. So if you look at your number line of homes, so I guess jumping on Daniel's example, say you have 2 and 8, you basically look at the middle of this range, and you basically note that when you place your lighthouses, you basically assign the left lighthouse to cover this range and the right lighthouse to cover this range. And what you essentially look is you iterate through your homes and find the home that's closest to the center. So if the red are all of your homes, you would basically find this house right here, and you basically say, okay, well, the power rating I need then, this blue one, is basically going to be this distance here, which say is like x, and you do the same thing with the right lighthouse. Basically, you also place it from the right house here. You say this is also x, and this will actually cover all the houses because this is the closest one to the center, right? So this definitely covers these 2. And the one left obviously also covers these ones because this is closest to the center. And this is actually order n, so this is actually quite cool. We didn't see that, but that's nice. I like it.
Surprised us. That was good. We learned something from this too.
So I guess, Daniel, do you want to go on to the infamous flights on Mars?
Yes, flights on Mars seem to cause a little bit of trouble for quite a few people. And there are 2 approaches you can take to doing this. A lot of people decided to go with a union find approach, which is perfectly fine. But for the approach that I took when I did this was using connected components. So anyways, I'll describe the problem quickly for those of you that didn't check it out. So basically, humans have inhabited Mars and they set up a bunch of airports. So let's draw airports as just circles for now. And right now there exists a bunch of flights, and you're given these flights. They're 2-way flights. And let's say, for example, our existing flights are in green. And I'm going to give myself one more airport that has no flights to it. So you're given how many airports, so in this case we have 6 airports, and then you give the existing flights between airports. So let's draw numbers in here quickly. 2, 3, 4. Ooh, I'm really bad at this. 5, 6. So you're given how many airports, and then you're given the existing flights. So there's a flight from 1 to 2, and a flight from 2 to 3, 1 to 3, and the flights go bidirectional. So if you're given a flight from 1 to 3, then you also know there's a flight from 3 to 1. And what you're asked is, given a budget of adding X flights, so you can add X more flights between any of these airports, how many pairs of airports will be impossible to travel between through air travel only? So basically what you want to try and do is optimize where you put your flights so that you minimize the amount of the number of pairs of airports that you cannot travel between. So what I mean by that is, for example, if you're at airport 4, you can get to airport 5, but you can't get to airport 2. And that's because there's no flight, and there's no series of flights you can use to get to flight 2. But keep in mind, you can be, like we're talking about it, like it's absolutely impossible to travel, so you can travel through any number of flights, but as long as you can get to some airport, then it counts as those airports being connected, or you can travel between 2 airports. So if we had like a bunch more houses, or not houses, thinking of the last question, so a bunch more airports, and they each had a flight here and here, it is possible to get from this airport to the second airport. Oh, sorry, I forgot to draw the last line. If these are all connected, it is possible to get from this airport here to the second airport. So it can be any number of flights. Oh, what did I just do? Oh, I just refreshed the page. LOL. I meant to undo. That's bad. Okay.
Okay, I'll erase it while you continue.
Okay, thanks. So yeah, so basically that's the problem we're trying to solve. And once again, like I said earlier, people decided to go with the union find approach. And that's a perfectly valid approach, because what we're trying to do is determine which airports are connected to one another and which airports are not connected to one another. So if you use union find, you end up grouping 1, 2, and 3 into one group in the union find, and then you could also group 4 and 5 into one, and then 6 will be by itself still. And then from there, through union find, if you're using weighted union find, you can figure out the size of each tree. So that gives you, for example, the size of the leftmost one here would be 3, because there's 3 nodes in here, and the second one will have 1, and then this one, sorry, 2, and then the last one will have 1. That'll be your weights. So that's the critical part, or that's like the algorithmic part of this problem, is figuring out how to group these and figure out how many airports are actually connected. So a lot of people use union find. I decided to use connected components. A lot of you probably know what that is. Basically, you just go through and you say, okay, I start at one node, and then I'm just going to use depth first search to figure out every single airport I can get to. I just traverse all of these edges to figure out how many airports I can get to. And then once I've exhausted all of the edges I can travel in this area, I can count how many nodes I've been to, first of all. And then I can say, okay, I know exactly how many nodes are in this group as a whole. And then I can continue doing that for all the nodes I haven't seen yet. So then I'll end up moving to this one. And then I'll notice, okay, I have these ones in my connecting component, etc. You do that for all of your nodes. So yeah, how you, sorry?
Go on.
Okay, how you go about grouping these nodes is completely up to you. Union find works, connected components works. But what you do after that is interesting. So basically, what we want to do is figure out, okay, let's say x is 0 for now, just for argument's sake. Let's figure out how many pairs of airports are impossible to travel between. Forgetting about x. X is 0, we can't add any more flights. Let's just figure out what it is off the bat. And the way you do that is you can take the sizes of all of your components, and you know that, for example, if you have 3 nodes in this one, none of these 3 nodes can get to this single node over here. And they can also, none of those 3 nodes can also get to here. So you're adding 3 twice to the number of pairs. So if you notice that since there's only 2 nodes in this component, this is just the same as saying 3 times 2. And then once you say, okay, look.
Well, sorry, the pairs aren't ordered, right?
What do you mean?
So like when you say 3 times 2, you mean because you're looking at each of the airports in the leftmost component and saying 3 of those, and there's 3 that none of them can get to, so that's why you're doing 3 times 3.
I'm not doing 3 times 3, I'm doing 3 times 2. So for each node in this group, there's 3 nodes in this group. Each node cannot get to this node here. So we have 3 nodes that can't get here, so that's 3. Same thing for this node here. There's 3 nodes over here that can't get to this node, so we add another 3. So that's 3 plus 3 here.
Oh, okay.
Yeah, sorry, that's 3 plus 3. But that's the same as 3 times 2. So we can see we're multiplying the size of one group to the size of the next group. So let's say we decided, okay, we do want to add, so let's extend and include this 6th node here. Basically, how should I explain this? Yeah, so you have 3 times 2 here. That's part of our solution. Let me bring it over to the side. Let's do, got 3 times 2. We know that's part of our solution. And that's just for these 2 groups here. Now we got to do the same for this group of 3 and this group of 1 over here. So we know we have 3 that can't make it to the single 6 node. So then that's 3 times 1. So we can add 3 times 1. And then we also need to account for the nodes here that can't get over here as well. So we got 2 nodes here and the 1 here, and that's, we add 2 times 1. And then in the end, if you add all those together, you get your answer, which is 6 plus 3 plus 2, 11. Is that correct?
Yep.
Okay, cool. So there's 11 pairs of nodes in here that don't have some series of flights between them. So that's how you calculate that. But now, let's say x is not 0. We want to figure out the best way to add new flights so that we minimize this 11 as much as possible. And the approach to this is just being greedy about it. So this is a greedy approach. Essentially, it's always best to take the 2 groups with the most nodes in them and put 1 road in between them. Now, why does this work? If we add 1 node here, so yellow is going to be our new x nodes. So let's say we add a flight here. It actually doesn't matter where we put this flight. It could be from 4 to 3, 1 to 5, 2 to 4. As long as it connects one node from one group to a node in another group, you're essentially making this, these 2 components one big component. And all you're doing here is you're adding the sum of these 2 groups. So now you have a group of 5 and a group of 1. So then your result becomes 5 times 1 for the number of pairs that don't exist. So 6 for every single one of these. So then your answer becomes 5. And it turns out if you always take the 2 biggest groups, you'll always come to the minimum answer. So this was for x is equal to 1. If x is equal to 2, obviously we'll just connect one of these nodes over here to the 6th node, and then you'll have, your answer will be 0 because everything is connected. But that's essentially the approach you take.
Yeah, so you connect like the biggest x plus 1 nodes.
Yeah, that's the idea.
X plus 1 components, sorry.
Yeah. I hope that was clear. If you have any questions, feel free to ask us in the chat. We'll try and keep an eye on it as we go. But yeah, that's the approach. If you want like a way more in depth, I went pretty crazy on the editorial, and it's like 500 lines of explanation, and it's a little bit more clear than what I explained out loud here. But yeah, this is the gist of it.
Yep, and shout out to LeMichael for being the first one to solve this completely.
Yep.
Yeah.
We didn't see any interesting solutions outside of what we already knew. So, yeah.
That's right.
All right, let's move on to quantum.
Okay. Yeah, I think this problem by far had the biggest variety of solutions. In particular, so the first person to get a full accept solution is, again, Yili Liu 7. And they're basically 3 approaches. So I should probably start by explaining what the problem is. Essentially, you're given a bunch of probabilities. So say you're given 3 probabilities, like 0.2, 0.3, 0.8. And essentially, what you want to do is you want to do 2 things. So you want to multiply them all together. I can't do this in my head, so this would be like, say, x. And then what you do is you subtract 1 from each of these probabilities. So like 0.2 multiplied by 0.7 multiplied by 0.2. And you want to compare, basically, is x greater than y? So the kind of interesting thing about this problem is that, like, conceptually, like, it seems quite simple. Oh, you just multiply the numbers and you get your answer. But the catch is that if you have like thousands of these numbers, your number is going to be really, really small. Like x is going to be like, like I don't know, like 10 to like negative like 100. Like it will fall outside the precision basically of what you can represent in most floating point types. So you need some clever approaches. So the simplest approach, which I mean, I personally don't really like it that much because you basically need to use Python for this. But there's actually a built-in library in Python which lets you basically have floating point numbers with arbitrary precision, and you can basically just cheese the problem by creating like numbers which have like basically say like 1,000 decimal places or more after the decimal point, and actually computing x and y literally using this library and checking if x is greater than y. I won't really cover too much of that because I feel like it's it's valid. If you did, that's fine, but it's not amenable to other languages. It's not really the algorithm that we were looking for. The intended solution, I should say, is to use logarithms. So this is used very often in machine learning. Essentially, if you have the product of a bunch of numbers like a times b times c, say times d, and you basically want some kind of representation of this number, what you can do is you can think about applying the logarithm of taking logarithm of this product. And basically, if you have a logarithm of a product of things, you basically get the sum of the logarithm. So you get like log of a plus log of b plus log of like c and so on. Oh, and log of d. And the idea is that here you're just adding logs, and the logs are going to be like floating point numbers that are, I don't know, between like negative 100 and 1 or something, or in 0. I can't do this math live. But then this just becomes a simple sum over, these numbers like xi, and you can basically compare the sum of like these. You can basically compare the sum of logs of these numbers versus sum of log of these numbers. And the reason why this works is a very simple fact, which is that if x is greater than y, then the logarithm of x is greater than the logarithm of y. So you can compare logarithms no problem if you just need to figure out which one's bigger. And so yeah, you just take the sum of these logarithms and you compare them and check one's bigger than the other. And that works. That's sort of the intended solution. And just, I guess, to finish this off, one solution which we saw, which was quite clever, that, again, we didn't really think about before. Actually, I don't think I actually wrote down who submitted it, but...
I know Yili Liu was the first one to do it.
Oh, okay, nice.
Yeah.
Yes, so the other approach is to actually normalize these probabilities as you go. So basically, the idea is that if you're just looking at computing x, what you can basically do is you can look at 0.2, and you can multiply it, say, by 0.3. And if this number is like too small, let's say this number is like, I don't actually remember what people use, but let's say this number is less than 1. What you could do is you can take this product and just multiply it by 10. So say now it's like 2 times 0.3. I guess that's still less than 1, so you multiply it by 10 again, and basically you end up getting like 6. And as long as you basically multiply the x and the y by 10 by the same number of times, you can still, again, compare, is x greater than y, or is it less than y? And this is like a really nice approach if you didn't think about using logarithms, because it kind of works. I don't know, I thought it was actually pretty clever.
This is genius.
Yeah.
You should have seen our reaction. Yeah. We were like, what? So yeah.
Yeah, very good. So yeah, that's quantum lottery. So Daniel, do you want to do pesky Roomba?
Yes, I guess that's the next one, isn't it? Okay.
Yeah.
So I'm on slide 6, by the way.
Okay.
Pesky Roomba. So this was a pretty interesting one. I think this is the most solved question. Well, the easy version was the most solved question out of everyone who attempted it. So basically, for those of you who didn't take a look, we essentially have a triangle in a room. It's a triangular pillar in the middle of the room. We're looking down to the floor, so this plane is the floor. And we have a Roomba. And this Roomba has been tied to one of the corners of this triangle. And let me just draw it out for you. Can I get a line? Oh, no lines. Okay. I'll just draw a really sketchy line. So yeah, it's tethered to one corner of this triangle. And the dimensions of this triangle, it's an equilateral where each side is of side length x, and then we're also given the length of the rope, which is L. And we're asked, how much area can this Roomba cover? So for the easy version of this problem, if you'll notice, the length of L is bounded, and the length of L is less than or equal to 3 times x divided by 2. So 3 halves of x. So that constraint is really important for the easy problem. That's because we know that the Roomba will cover, I'm going to have to draw this somehow, it'll cover all the area up until here, and then if the length is exactly 3 halves, it'll end right halfway on the second side, because we're just taking half the perimeter. Same with this side, it'll go all the way around, but then it'll land, oh that's not even close, but it'll land right at the same point. So there's no overlap between the sides it can go around. So for the easy problem, this made this a lot easier than the difficult problem, because in the difficult problem, we don't have this constraint. So you can actually overlap quite a bit. So you can have the Roomba going over here, and then the Roomba over here, which makes it a lot more tricky. So let's solve the easy one first. The first thing to notice is if L is less than X, we know that the radius is not going to pass over the corner. So we essentially just have a pi. And this pi is very straightforward because since we have an equilateral triangle, we know this is 60 degrees. So I'll draw 60 here. So we know that the circle is, 5/6 of, sorry, the area is 5/6 of a circle. So you can take 5 over 6 times the area of the circle, which is, let me actually write that up, pi r squared. In this case, r is L. It doesn't show in this diagram here, but let's say the Roomba is here instead. L would just be r, so it's actually 5/6 pi L squared. And then that would be your answer. Now, when it goes over the edge, that brings up an interesting scenario. What happens when we go over the edge? So let's see if I can get rid of this. Let me draw the 60 back in. 60 degrees. So what happens when this actually goes over? Basically, what ends up happening is as soon as you cross this point, so let's say it's a dotted line here, as soon as you cross this point, your radius changes. So now your radius goes from whatever L is, so we know L will reach, let me grab blue again, would reach all the way out to here from this corner. This would be L. And we know that it changes because we're losing x distance. So we end up having L minus x for our new radius. And how much do we use that new radius for? Since this is the easy version and we know it's not going to overlap or anything, we know what this angle is because it's 180 minus 60. You can easily calculate the area of this arc here. So you can take, what would that be? That would be 2/6. Yeah, 1/3 of a circle. So you just, yeah. So essentially what you end up happening is, if you take into account the other side as well, you know you still have that, oh my goodness, 5/6 of your full circle, pi r squared, pi L squared. And then we're going to add on whatever's left in this area, and we know what this is because we can say 2 times, since we have 2 of them, we have, x, we have 2 here, right? And then we can just say it was 1/3 of L minus x squared, of pi L minus x squared, I think. Please correct me if I'm wrong, Mikhail.
I think that's right.
I think that's right. So yeah, so you just add this one to this one, and you get your answer for the easy problem. Now, the overlapping problem. This is not obvious right off the beginning, so let me just erase all of this and chicken scratch here. So it's basically this solution requires seeing an insight. We need to figure out a way to account for this overlap, or not double count the overlap. So let's see if I can draw this out nicely. I can't erase a circle? Can I move it? Yes, okay. Let's bring it in a bit. And we have our tether a little bit, oh, that's too small. Oh, excuse me.
We can use our imagination.
Yeah, I guess so. I guess I can make the triangle smaller, can't I? Nope, I can only rotate it. Oh, I can do that. Let's make the triangle smaller, it'll make my life easier.
Okay.
This is still equilateral, even though it might not look like it is. Just bear with me while I make this a little bit more readable. And then we can move this out a little bit more.
Okay.
Yeah, good enough. Okay. Yes, so this is our situation now. We still have our x here, We still know it's 60 degrees. I'm not going to write that in, but we still know it's 60 degrees. Now, if we were to draw out our circle, it'll come around and then it'll go something like this. And same thing for the opposite direction. Something like that, and then once we hit that corner, it'll bring it in a little tighter, and then there. But now we have this overlap area, which it's a little bit tricky to figure out exactly what we need to do. But basically the insight you need to make is that you can actually split this area into another triangle. So basically from this point where the two lines meet to the corners of the triangle, you can figure out exactly, well, basically you can break this area down into smaller pieces. So what ends up happening is you have this triangle here, the green triangle, and then you also have, if you extend this line up, you have that point where you have L minus X. Extend this as well, L minus X. And we know that this will have the angle between this green line and this red line here. So then what ends up happening is you once again have the area of this big circle, and then you can calculate the area of this pi here, which is also equal to the area of this pi here, and then you can calculate the area of this triangle here and add all those together, and that's how you get your answer. I'm not going to write out all the equations for it, but the way you actually acquire the values for this triangle in the middle is just basic trigonometry. I'm not going to get too deep into that because I'll probably screw it up, but if you go to the editorial, it's pretty verbose on how you actually acquire these values. But the insight is mainly what the problem was, figuring out the trigonometry. It kind of goes back to just high school math. There is one law that you could have used to make your life easier, but it wasn't mandatory, and that was Heron's law. And that's for calculating the area of this triangle in the middle without having to, well, just by knowing all of the edge lengths. You can calculate the area of a triangle using only the edge lengths. And in this case, this edge is actually equal to this edge, and then you know this edge already, so it's actually pretty easy. So you can use Heron's law to make your life easy, but it's not mandatory. That's what I used in my solution, but there's many people who didn't use it. They just use a different approach with trig to figure out the area of the triangle.
Yeah, I think if you actually sort of break it down symmetrically, so instead of having 3 triangles, you basically have 4. So basically if you take your green triangle and you split it up into 2 other triangles, you can just get away with like Pythagorean theorem, basically.
Yeah, that too.
Calculating this area separately from this one. But it's basically the same approach.
Yep.
Yeah. Should probably also mention Pesky Roomba, Wyatt Wismer was the first one to submit full AC solution on the easy version, and I guess Alicia Tran 4550 was the first one to get the difficult. And in this problem, we also kind of noticed after the fact that I guess this is sort of our kind of mistake. We had sort of a few, we didn't sort of foresee this, but in that easy, basically the easy version of the problem, there was only one test case out of the samples which had, I think, L extend past length of the triangle X.
Yeah.
So people could actually get most of the points by just doing the 5/6 pi L squared.
Yeah, there's also an issue. We also noticed that there's quite a few people who took their solution for the easy problem and submitted it to the difficult problem, and the amount of points you'd get from submitting the easy solution to the difficult problem is greater than the amount of points you could have gotten from the easy problem for having the correct solution. So that was also an oversight on our part. We didn't think that through too much. But yeah, we don't think it affected the outcome of the contest too much. I think most people saw the difficult.
Some people caught on to that.
Yeah, most people did.
Yeah, nice.
Awesome.
Right.
Virus Royale is next.
Yeah. Okay, so this is I think the most difficult problem which we actually had a correct submission for, and that submission goes to Wyatt Wismer. Virus Royale is basically a problem of probabilities. I didn't really mean for that to be a bit of a theme in my problems, but I guess that's kind of what it turned out to be. So basically, the idea is that you have, say, some group of viruses of type 1, another group of viruses of type 2, and another group of viruses of type 3. And the idea is that in Virus Royale, what you do is you basically almost do a simulation where with uniform probability, you pick 2 random viruses from these groups. So let's say you take this red one and this green one, and they basically like fight each other. It's a gladiator style. And there are certain rules. So basically the rule is that like if a virus from team 1 and team 3 meet in a duel, then the virus from team 3 always wins. If a virus from team 2 and team 3 enter a duel, then I think the virus from the blue team wins. And if these 2 enter a duel, then the virus from the green team wins. So let me actually just, for clarity's sake, erase this here. So what you want to figure out actually is what is like the last group standing. So eventually, after you run the simulation for enough time, you'll either have one of 3 scenarios. Either A, you're going to have 1 green virus left, B, you're going to have 1 blue virus left, or C, you're going to have 1 red virus left. And the idea is that is if 2 green viruses fight each other, 1 of the green viruses wins. Doesn't really matter which one. Same with red and blue, and red, blue, and green. Sorry. So how do you do this? How do you solve this problem? Well, the key insight is actually to look at the constraints. So constraints basically say that the max number of viruses in each group is 100. You can have at most 100 green viruses, at most 100 red ones, at most 100 blue ones. And then you can actually use a technique called dynamic programming to solve the problem. So what you basically can think about doing is you can think about creating a function that's called f, which takes in 3 numbers. So the number of green viruses, the number of blue viruses, number of red viruses. And this basically computes the probability that, say, the green team wins. The probability the green team wins is sort of can be recursively defined. By the way, Daniel, apparently the Jamboard is frozen.
What?
So, well, yeah. So basically, you have this function. I'll guess continue describing it while we go on, and then when it unfreezes, you'll be able to see the actual solution. But
Okay,
you basically see, okay, nice. If you basically go through each of the possibilities of what's chosen and see what's probably the green team wins. So basically say, okay, if 2 green viruses are chosen, after they duel, there will be 1 less green virus remaining and the same number of red and blue. And you basically multiply this by the probability that this happens. So in this case, this is like, say, the number of green divided by a total number of ways to choose, which I'll just call Z. Another possibility, so let me just annotate this actually. So this is like 2 greens. If you have like a green and a blue, let's say, then in this case, the winner is actually, you know what? Let me choose blue and green and red just to make this line up a bit better. We have like green and a red here. Then basically we have, well, the green virus is the one that's eliminated again. But the probability that this happens is actually a bit different because instead of just basically doing like number of green viruses choose 2, you instead have like, actually I should probably write it like this. You basically have the number of green viruses times the number of red viruses. And over this like normalizing factor. And you basically go through all 6 possibilities. So like green, 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 red, 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 blue, 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 green. And you basically just save your answers for each of the Fs. And that's basically how you get the result. Because we actually are looking for the probability that each of the teams, probably each team wins, what we basically can do is we can actually just like solve this problem for green, and then just swap around these numbers because the problem is kind of symmetrical that way, and solve it again for red, and then swap these numbers again and solve it again for blue. And that'll actually work out. And the complexity of this solution is basically n1 times n2 times n3. This is basically how many states you can have. And yeah, the way you calculate Z, by the way, this normalizing factor, is you basically just add the probability of, or basically add the total number of ways you can choose two viruses. So in this case, this is like, you basically can just add all of these numerators. So it'd be like, put it this way. So this is like choose. So number of green, choose 2, plus say number of red, choose 2, plus number of Wait, when I say green red, this is actually like N1, N2. And this one will be N3. This is number of blue, choose 2. And you add this with, like, again, you choose a green and you choose a red. Or you choose green, choose a blue. And just to finish this off, if you choose a red and you choose a blue. And yeah, this is basically your Z. And yeah, so this is just like 3-dimensional dynamic programming.
Nice.
Yep.
All right. I guess it's time to move on to the 2 problems that no one answered.
Okay.
Unless you have anything more you want to add to this.
No.
All right, cool. So I guess we go to ramen time now.
All right.
All right, so ramen time. This one's a pretty interesting problem. Sorry, just lost my words. No one managed to solve it fully. We do have some people who managed to cheese some points out of this. So the people who managed to cheese a bit basically just returned the maximum recipe time. And that was a pretty smart thing to do because, I should explain the problem first.
What's the actual problem?
Yeah, okay. So basically you're told the number of pots that you have in a kitchen, and you're also given a bunch of recipes. And your goal is to cook all of these recipes in the minimum amount of time. So we have 5 pots here. Let's say we're given 6 recipes. You're given the times of each. Not necessarily unique and not necessarily different. Let's say we have 6. Let's say they are 1, 1, 2, 3, 5, 6, just for argument's sake. And this is the amount of time it takes to cook these things. So you want to figure out which recipes to put in which pot at which time so that the minimum amount of time for everything to be cooked is minimized. So in this scenario, let's just try and solve it manually. Let's give 6 to this pot here, 5 to this pot, 3 here, 2 here, and then we'll put both 1s in here. So this would be 1, hold on, it'll be 1 plus 1. You can't cook 2 things at the same time. 1 plus 1. It's important to note that it takes no time to switch out recipes. So this is what the optimal solution would be for this problem. And obviously the maximum amount of time it would take, since these all cook in parallel, maximum amount of time it would take is 6. So a lot of people just said, okay, if I take my recipes array and return the largest number, chances are that's going to be the answer. And I think people managed to run away with like 16 points out of 50, I think, with that solution. So kudos to them for finding that loophole. But nobody was able to figure out the perfectly optimal solution. And basically, there's a number of ways you can approach this. During our testing, we had our external testers test this out. Each person came up with their own different way, I think, to solve the problem. Some used binary search when others didn't, and then there's a bunch of different approaches. But the approach I'm going to talk about is basically pruning. It's going to be like pruning the problem's space, essentially. So basically what we're going to do is we're going to take a brute force solution, and then we're going to try and take shortcuts wherever we can when we know that proceeding down that branch or into that, like down that path won't actually benefit us. So there are 2 things that you can do. So first of all, I'm just going to go over very briefly what the brute force looks like. I'm not going to write anything out. There's really nothing I can really draw. I'm just going to explain it, maybe put jot notes down here. But basically, what you want to do is see, can I put this recipe, hold on, let me gather my thoughts here. It's kind of hard to explain this. So is it...
I guess it's almost like you iterate over, like, in some sense, you iterate over the recipe, and each step you basically check to see, like, which pot, like you try and put it into each of the pots, right?
Yeah, so basically you take each recipe and say, can I put it into pot I? So this is pot subscript I. Let's make I a little bit smaller. I. Can I put recipe in pot I? And basically what you can take a look at is, if I put this recipe in this pot, will it make my my best solution so far worse? But basically you try putting every recipe in every single pot. Sorry, yeah, I'm explaining the brute force first, yes. So basically, your brute force is for every single recipe, you try and put it in every single pot. and then you move on to the next recipe, and then you try and put it in every single pot again, and then you basically end up with, if you weren't to optimize this at all, I think what you'd end up with is O of the number of recipes to the power of pots. Mikhail, please correct me if I'm wrong. I'm really bad when it comes to powers.
Oh,
it's
I think it might be
exponential,
the
not what.
opposite.
It's the
Yeah,
opposite?
I think it's p to the power of r.
Okay, p to the power of r. Either way, it's too big. With the constraints you're given, both of these numbers can be 16. 16 to the power of 16 is crazy. Very, very, very big. It'll take way too long to compute that. So we're going to come up with different ways to make it so that there are certain paths we don't need to go down. We know we don't need to try putting this recipe in this pot because of something I learned earlier, and I know if I were to put this recipe in this pot, there's no way I would get a smaller time than I've seen so far when I've tried putting other recipes in other pots. That was kind of a whole jumbled explanation. But there's two optimizations we can make. So the first one is, let's keep track of the current recipe, or the current worst time I have so far. And that worst time is basically by just taking whichever pot has the maximum cooking time. We can take that current time and say, is my current time worse than the best time I've seen at this stage? So if you're looking at the fifth recipe and you've already assigned recipes 1 through 4 to pots, and you know the maximum amount of time you have from those 4 pots is worse than a different maximum of time you've seen for those 4 pots, there's no point in continuing. So if the current is greater than my best, there's no point in continuing. Because no matter what you do, you're still going to have that worst time. Once you've already assigned recipes, you can't take them out later. So if your current assignment is worse than the best you've seen so far, then there's no point in continuing. Period. That's essentially the first optimization. And by doing that, you end up cutting down the problem tree a lot. So you don't end up doing work that doesn't benefit you. The second optimization is kind of harder to explain. But basically think of it like this. So let's think of a small example. Let's say we have, let's say we have 3 recipes and 3 pots, for example. So let me grab a different color. So we have 3 pots, and we have 3 recipes. It doesn't matter what the time of those recipes are. Let's just say R1, R2, and R3. If we assign recipe 1 and recipe 2, such that, let's say the first time we're going to make it so that pot 1 has R1, and then pot 2 has R2, and then we haven't assigned recipe 3 yet. We haven't assigned recipe 3 yet. So we're trying to figure out recipe 3. If we've seen this situation, we know our maximum time is going to be the maximum of the first recipe and the second recipe, right? So once we continue down and we've added 3, we've seen what the worst is, and we've tried adding recipe 3 to all the pots, blah, 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 blah. We've tried all that. Eventually we're going to end up in a situation where we have the same 3 pots again, and we're still trying to figure out our 3. And we've assigned the second recipe to this pot and the first recipe to this pot. What's important to notice here is that at this point, it's guaranteed that the maximum recipe between these 2 situations is the same. And since we know that if we have the same result at this stage, and we're still just trying to figure out where to put our 3, if we've already computed this once, so if we've already computed this the first time around, there's no point going around and computing it again, because we're just going to end up with the same result. We're going to process the same information in the same way. Since we can't take out these recipes, and we know the maximums are the same, there's no point in going further. And this happens to be like the biggest optimization, because you end up cutting out huge sections of your problem tree. However, there are test cases that kind of make this optimization mute. Like if, for example, if all of your recipes were a power of 2, then this optimization would never occur. Actually, is that the case? Oh, maybe not.
I don't think so. I think it's like you can't like the thing you described. I think that's still valid for powers
Oh,
of
no,
2,
yeah,
but
you're right. Okay, why was that?
there are other things which
maybe that's a different problem. So yeah, for this case, these are the 2 optimizations you make. And by pruning your problem set using these two optimizations, you end up bringing down this runtime into something that's more manageable. Now, what that runtime is, the worst case runtime, we still haven't really figured that out. When it comes to pruning problems, it's kind of difficult to figure out what the worst case is. But it's fast enough so that it'll pass HackerRank's test cases. Now, there's actually another approach you can take to solve this problem. There's many approaches, but the main gist of the other two approaches is one of them is bitmask DP, which is pretty complicated and it's kind of an advanced topic. However, it does solve the problem, albeit not as efficiently as this optimization prune. But it does solve the problem, and it solves it in apparently in O3 to the power of I think it's R in this case.
Yeah.
Times
so.
P. Maybe P and R might be switched. I don't know why I'm struggling so much.
No, I think you're right. You're right.
Okay, yeah. So this is the runtime. If you were to take 16 and 16 for this test case, you'll notice that the number is actually still really, really big. But for some reason, it still runs on HackerRank and really quickly. It's like sub 1 second. You can still get that optimization. Mikhail, you had a different approach using binary search. Do you want to describe it briefly?
Yeah. I'm not going to draw it out, but it's somewhat of a variant of your pruning approach. Basically, what you do is you ask yourself, okay, what is like the best case time I can use to cook all the recipes? And essentially, your best case time is 0. Everything's already done. Your worst case time is going to be something like, like the sum of all the values, sum of all the recipes you're given. And so you binary search, and basically, for each time t, you ask yourself, is it possible for me to arrange the recipes in such a way that all the pots finish, before or at time t? And what you essentially do is you basically just do sort of like a brute force depth first search with some memoization. So you try to make it smart. You try not to like basically count things more than once. Basically do like in some like not exactly pruning, but you don't try and redo work you've already done before. And then you basically just do a depth first search where you basically like try and assign. You go again through all the recipes, try and assign them to pots, and basically as soon as like you can't really, as soon as you realize that you're stuck, like you made a bad assignment, then basically back out and try again. And yeah, this solution works just fine C++ and PyPy. But the binary search, I think when I did it, maybe I could have done better, but it didn't actually work as well in Python 3 or Python 2. Yeah.
Interesting.
That's right.
On to the last one, the advanced problem.
Yeah, so this one is under pressure. I think someone might have gotten a few points on it, but there were no, I think like, no one who was really close to the intended solution, which is fair enough. This is like a pretty tough problem. Yeah, so under pressure. So in this one, you're basically on a submarine with a rectangular plate along its bottom. So I'll just draw this out. It has a certain number of rows and a certain number of columns. And you might be asking yourself, wait, why is this a submarine? It's because there are holes in this plate. So specifically, there are K holes. This is kind of important. There are K holes, but you know the locations only of K minus 1 of the holes. So you have a hole here, and a hole here. The fourth one you don't know. And so in this case, K is equal to 4. You don't know where the fourth one is. And basically, the rule is that at time equals 0, wherever you have a hole, there is water. Each second thereafter, each basically cell in this plate that's connected to a hole with water becomes flooded. So after 1 second, everywhere where there's a green and blue in this case becomes flooded. Again, this is like, there's actually a fourth hole somewhere where you don't know where it is, but it's also contributing. But just for the sake of example, I'm only showing 3 of these. After another second, basically, these ones will also become flooded, and then these ones. So basically, after like 0, 1, 2, 3, 4, like 5 seconds, the whole plate will be flooded. And your task is to figure out, basically, given a very pessimistic estimate of where the fourth hole is, what is like the smallest amount of time that can elapse before the entire plate is submerged. So in this case, for example, it took like 5 seconds for this plate to be covered. But if you had a fourth hole, if the fourth hole was, for example, at like this location, then let's see, then this will be covered, this will be covered, this will be covered. Then actually after just 1 second, the whole plate will be covered. Well, actually, wait, sorry, I messed up. After 2 seconds, the whole plate will be covered, right? So the red is basically what will be covered after 1 second, and the second will just cover this strip here. So the approach to the problem is basically, it's sort of like a binary search with a line sweeping algorithm. What you want to do is you do a binary search on basically the minimum number of time it will take to flood the hull. And your task is basically to figure out a function that says, is it possible for the hull to flood in t seconds? So what you do is you basically take each hole, and expand it basically in each direction by size t. So let me actually draw this a different way. So if you have a hole here, after t seconds, you basically know that it will cover t squares above, t squares below, t squares to the right, and t squares to the left. And so if you have if you sort of zoom out a bit and look at your hull, you basically have these like squares, which might overlap, which look like this. And the idea is that if the union of overlaps of all these squares cover the entire hull, then you're done. You know for sure you can do in t seconds. Doesn't even matter where you put the kth hole. However, if you have a dry spot, so let's suppose, if for the sake of example, I will change this a little bit for the hull to be like this. So basically, in this case, you might notice, okay, you have a dry spot. Well, okay, actually, let me change this again just a little bit. Again, just for illustrative purposes to make the solution a bit more clear. Let's say that the hull goes like this. What you do is you essentially look at the dry spot. So in this case, the dry area is like what's in red here. All this area is dry after 2 seconds. And what you do is you find the leftmost column that is dry and the topmost row, which is dry. And basically, what you can think about to yourself is that if it's possible for the hull to flood, given k holes, you know that wherever you put the kth hole has to reach this top row in t seconds, and it has to reach this leftmost column in t seconds. And so an optimal placement is actually greedy, where you basically put the kth hole like t sort of cells to the right of the leftmost dry column, and t squares below the topmost dry column. So it would be here. And then you can basically add this sort of square to your hull and see, okay, is it flooded now? And now if it's not flooded, so in this case it would be like, well, things aren't really done to proportion here, but in this case, let's say the hole is like this. All the squares will be the same size, but suppose it looks like this, then you know, okay, the whole hull is flooded, so we can do it in t seconds. Let's binary search down. The only sort of tricky part is, okay, well, how do you actually find these dry rows and columns? How do you actually know if the whole hull is flooded? And for that, you use a line sweeping algorithm. So you sort of look at the example I've drawn on the right. You can actually think about this as a series of events. So your first event basically occurs here. And you can basically just figure out, okay, what is like the topmost and bottommost row that's being covered at, say, this x coordinate. And, well, you know what? It'll be easier if I assign numbers. 1 sec. So if this, for example, is like 1, 2, 3, 4, 5, at time, and actually, let me also do the x's here. So if this is like x equals 0, x equals 1, x equals 2, x equals 3, x equals 4, x equals 5, well, let's say 8. And you basically have an event that basically says, okay, at x equals 0, we know that we basically adding an interval from 3 to 5, and then at x equals, well, okay, I messed up a little bit here. Let's suppose, actually, yeah, this is 2. Yeah, so x equals 2, we're basically subtracting this interval. You can basically go across the x's from left to right. So here we're subtracting, here we're adding. And basically maintaining the intervals which are currently active, so where the squares are currently like on, you can basically figure out, are there any dry squares in this current like column? And if there is a dry square, then, well, you can basically, as soon as you reach like a dry cell, then you know that's the leftmost column that's not wet. You do the same thing. You actually just transpose this hull and basically do exactly the same algorithm, figure out, okay, what is like the topmost row that's not filled. They can place the kth hole and then line sweep through everything. And the idea is that basically at each time you either add this like square hole, or basically every time you add an interval or subtract an interval, you basically check to see, are there any dry cells in my current column? And if there are, then you basically stop. If there aren't, then you keep going. And if you reach the end of the hull and you haven't found any dry cells, then you're good. Yeah, so this is like an advanced problem. Line sweeping algorithms in general tend to be hard problems, and we kind of threw this in as sort of like a fun thing, I guess you can try and do on like a hot summer day. You have nothing else, just drinking iced tea. Yeah, so that's basically Under Pressure. I guess for more details, you should probably look at the editorial code. I think it sort of explains exactly what you need to do to solve the problem, and yeah.
All right.
That's the problem set.
That wraps up all the problems. All right, I guess we can pull Wyatt back in if he has any closing words.
Sure.
All right, Wyatt, join our call, I think. It'll take him a couple seconds. But yeah, let's we can switch back over to our cameras. All right, yours isn't showing. It's fantastic. Oh, there we go.
So we should probably
There he is. Hold on.
Hey.
Welcome back.
Hold on.
Enjoy the editorials.
Good.
I can't believe I made that mistake on the Mars question, though.
You can't either.
I tried to do my union find like off the top of my head, and I paid the price for it.
Yeah, you forgot to check if you're in the same group already.
Yeah. So then, see, normally it's not an issue because normally I don't store the sizes, but if you store the sizes, then it increases the size if you do that, and then you get the wrong answer. Yeah.
That's right.
Sneaky.
Oh, we were looking through your code trying to figure out why it was wrong too. And then you were like, "Are you sure there's no overflow?" And then I had a small panic attack. I'm like, "Oh." No, but I checked.
I was so confident because I was like, on the bottom code, I was like, "Yeah, it's definitely this." It's like it's so reminiscent of what is it, problem F from ICPC a few years ago.
Yeah.
Similar, yeah.
I thought it was all similar to like Maps 2020 with the roads. Basically, again, you look at the pairs.
Yeah.
It's a cool problem.
Thank you.
Yeah.
So I guess we should once again say congratulations to Wyatt, Michael, and Alicia for getting first, second, and third place, and of course the other contestants in top 15. Yeah, well done.
Yeah, thanks everybody for coming out. I hope you enjoyed these questions. I guess everything stays up, and I guess this video will be posted. So if you ever want to go back later and like go through the problems or I don't know any of this stuff, like it's all here.
We highly recommend you do. That's how you learn.
That's how you learn. Oh, there's a fun word. So I like to say that competitive programming doesn't actually have that much jargon. Like most of its jargon is borrowed from like just CS or other things. But the one piece of jargon that competitive programming does have is this word called upsolving. So I guess upsolving is a word that means to go back to a contest after it's done and solve the questions that you couldn't get full points on.
Yeah.
I guess that's how you really improve.
Yeah, it's also really nice because if it's especially a contest which you've already like done before, you sort of know like, well, after this contest you're better than what you were before.
It's like you can do something you couldn't do. Like you're just
exactly. Yeah, 100% the best way to learn.
To that end too, like this year we got. I mean, I haven't looked at them yet, but I imagine the tutorials are quite nice based on your descriptions from tutorials. So if you guys can always check those out too.
Yeah, we put quite a bit of effort into the editorials so that you can come back and figure out what's going wrong. You can see our code. I think every single editorial has two different approaches or two sets of code, most of which are in C++. So sorry for those who don't use C++, but you should be able to bring it over to your language.
I was actually curious too. The graphics were really nice. What did you make those in? Like GIMP or?
I made the pesky Roomba ones. I made on what's the name of that site?
GeoGebra?
GeoGebra, yeah, that's the one.
Yeah.
Nice. Yeah, I use PowerPoint for mine.
Actually, I completely understand. Like Microsoft PowerPoint or Google Slides.
Microsoft PowerPoint.
Microsoft, interesting. I'm a Google. I do most of my promotional art in Google Slides. No,
Oh,
sounds
nice.
horrific, but I actually like it for making like problem art.
It works.
Yeah.
It does.
Yeah.
Simple shapes.
Exactly.
Okay.
Cool.
All
I
right.
think that's everything. I guess we'll reach out to all the winners.
Yeah.
Yeah, I guess for anyone who doesn't know, like our ICPC regionals, which is the next stage, will be on March 6th. So I guess we have until then to train. So like we'll reach out with like training details and prizes and all that stuff.
Cool.
Yeah.
Awesome.
When is I guess you said March 7th, right?
Oh yeah, wait, March. I might be wrong. I'm 70% sure it's March 6th. If not, it's within a day. It's within a day of that.
Okay.
All right. That's fine.
Yeah.
We'll be watching.
Nice.
We'll be watching. Watch the leaderboards.
Yes. It'll be good.
Right.
It'll probably be on. I don't know if anyone has looked at last year's contest, but the regionals are almost always hosted on this site called Caddis. So you can always check out Caddis if you want to see it.
Yeah, definitely get used to the Caddis. It's much different than HackerRank.
HackerRank, yeah.
It's not hard to use though.
Cool.
Okay.
All right. Yeah.
All right.
Awesome.
All right.
Yeah, well, I guess we hope you guys enjoyed the contest for the problems. Hope you guys upsolved the ones you didn't get.
Yeah.
Yeah. Do you have any closing remarks, Daniel?
No. Thank you.
Or why?
Hope you enjoyed.
I should say wait before we actually end. I should say a big thank you to like Daniel McHale for like I don't know putting together all these questions, doing all the art, doing all the like the nice flavor text, I don't know testing everything and trying it out. Like,
I had a lot of fun doing it.
thank you
So
guys. Yeah.
Yeah, it's a good time.
yeah.
Cool. And I guess that's all. Yeah.
All right.
Thank you everybody for